All right. Hi. Today we're going to be going over the final exam for Argo 2. This is the 2016 spring exam. So, to start, in this exam, you're not going to have a facts section. It's going to be replaced with the ACS portion of the. So this exam is just going to have the nomenclature reactions, mech, synth, and then spectrum. Facts? Really? Oh wow. 6 points. Am I not recording? Thank you. I appreciate that. It's recording, like the screen. How's the screen now? Good. Okay, appreciate it. I think she might be two. It's six. Oh, it's only one. Okay, 6 points for one facts question. Okay, I guess not too bad. I guess on this one we're not gonna be going over any facts, but I think potentially afterwards. See. So, um, so to start, we have the nomenclature section. So, for the first one, we have some a pretty long chain from excuse me. We have a pretty long to start. We have a pretty long chain coming from the right side over 1, 2, 3, 4, 5, 6, 7, and 8. So we have an 8 carbon chain there. We can also number it backwards. So that's gonna be our longest chain. So if we were to number it backwards, it would be so to start. If we look at where the substituents are on for the first way that I wrote. Actually, I should have chosen different colors. My bad. Let me change the color real quick. So in the red way, we have substituents at carbon 3, at carbon 6, and that's it. And with the blue way, we have substituents at carbon 3 and carbon 6 again. So on both of them, we have the same subs. Yeah. So on both of them, we have the same numbers. So we're gonna keep going. Um, whenever we keep actually sorry, we have two substituents on carbon 6 for the red numbering. So for the red numbering, this is diethyls on this nitro group. So it's gonna be actually 3, 6, 6. While for the blue we have 3, 3, 6. So because of that, we're gonna be going with the blue numbering for this. So the blue numbering is gonna be for the parent chain. And then whenever we start the parent chain, we're gonna start with the parent. So for the parent, our chain is gonna be called it's an octane chain. So we can start with the octane, I guess. Octane. But then we know we have to put the amine as this part as the parent. So because this is gonna be our highest priority group. So what's it's gonna be called is the octanamine. So instead of the E at the end of octane, we're going to put amine at the end. And to specify that it's on carbon 3, we're going to put 3. So 3-octanamine. And then, so that's our first parent. So now we can go into subs. So for our subs, we have 3 subs. We have 2 ethyl groups off of this N, and then we have this benzene ring connected to a CH2. So remember, whenever we have a benzene ring connected to a CH2, this is going to be called a benzyl as the substituent. Whenever we just have the instead of the CH2 right here, we just have the straight benzene ring like this. This would be called a phenyl. So what we have here is a benzyl. So on this one, we can say that carbon 6 has a benzyl sub, and then on carbon 3, or not carbon 3, for the end, since we have the 2 ethyls on the ends, it's actually going to be N comma N diethyl. And then we don't have any stereochemistry for this, so now we just have to put it all together. So we can start with the alphabetical order. So the B for benzyl. So we're gonna start 6-benzyl dash N comma N dash diethyl dash 3-octanamine. Are there any questions on that one? Yeah. Yeah, you can so you can put a diethyl octan dash 3-amine. Yeah. What do you mean? Oh, like NN before the N 6-benzyl? No, because we would actually have to go by alphabetical order in this one. Yeah. Anyone else? Okay. And then okay, so moving on. So in this one we have an ester. So this is going to be our parent chain. So we have the ketone, the ester, and the ether right here. So we're going to have three different groups, but our ester is going to be our highest priority. So that's going to be our parent. So remember, whenever we're naming the ester, we have two different kind of names because we actually instead of putting dashes in between them, we put an actual space. So to start, um, if we count this 1, 2, 3, 4, 5, and 6, we have a 6-carbon chain. This is going to be like I guess our parent kind of thing because it's going to be going at the very end, right? And then the side attached to the oxygen. This is going to be our at the start of the name. So 1, 2, 3, 4. This butyl chain is going to be attached to our is going to be at the start. So if we were going to name the parent, I guess we can start. We have a substituent on the third carbon, and that's going to be a 3-oxo. So we're going to start 3-oxo dash not dash, I guess 3-oxo and then hexane. So one thing we need to remember is that whenever we're naming esters is that the E is dropped and then we add O8 at the end. So this would be instead of 3-oxohexane, it would be changed to 3-hexane O8. So that's going to be telling us that we have an ester. So and then for the left side, we have a butyl chain, and then we have a OCH3 at the end. That's going to be called a methoxy group. So we have the oxy meaning the O, and then the methoxy being the chain coming off of the ether. So if it was like a longer chain, like an ethyl, it would be like an ETH oxy, so an ethoxy, right? And then propoxy and so on. So we have a methoxy here, so we can start with 4-methoxy. And then we have the 4-carbon chain, so it's going to be a butyl, 4-methoxybutyl. And on this one, we don't have any stereochemistry, so we can just put it all together. 4-methoxybutyl. Making sure to put the O side of the ester chain first. And then instead of the dash in between, like I said previously, we're going to put a space, and then we're going to start with 3-oxohexanoate. And that is going to be our name structure. Are there any questions on that one? All right, going to the next one. So in this one, we have two candidates for our parent chain. We have the N and we have the OH. In this one, the OH is going to take priority over the amine. So our the alcohol has a higher priority than the amine. So we're going to start by trying to put the alcohol into the parent. So if we're gonna start numbering, we could start numbering from two ways: 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then we also can start numbering the opposite way, which is going to be 1, 2, 3, 4, 5, 6, 7, 8, and 9. So in both chains, we have the alcohol on the fifth carbon. So in the first chain, we have in the blue numbering, we have the substituents at carbon 5, at carbon 9, and at carbon 9. And in the red numbering, we have the substituents, not including the oxygen, on carbon 1, and carbon 5. So we're going to be going with the red numbering as the correct numbering. So we'll erase the blue. And now moving to start, we can start with the parent chain. So our parent chain is going to be a nonane. So nonane. And then because we have an alcohol on it, it's going to change from nonane to nonanol. So we're going to drop the E, add the OL. So nonanol. And to indicate it's on the fifth carbon, we're just going to put 5 before that. So 5 nonanol. And then our substituents. So we have 3 substituents on this. So for the N substituent, we have 2 N ethyl groups. So whenever we have that as a substituent, this is going to be called a diethylamino. So we have 2 ethyls on this. So we're going to say carbon 1 diethylamino, 1 dash diethylamino. And then on carbon 5, we have our CH3 methyl group, so 5 dash methyl. And on this one, we have stereochemistry. So for our stereo, we're going to start by, we have the chiral carbon right here. So we're going to choose between R and S on this. So we know that the oxygen is going to be our highest priority. Then we have the choice between this CH and this CH2, this CH2 and that CH2. So on this CH2, we have 2 hydrogens and the carbon bond. So H, H, C, and this one is the same. And C. So if we keep moving forward, this one and this one, actually, I'll go by different colors. So in the purple, these are both the same. They're bonded to 2 hydrogens and a carbon. And then the light blue, these are also the same. They're bonded to 2 hydrogens and a carbon. And now for the last one, we have our 1 and 9. And this hydrogen, so the nitrogen, and then 2 hydrogens. And then the 9th carbon is bonded to 3 hydrogens. So because of that, this is going to be our second priority group on the left. And our third priority group will be where carbon 6 is. So 3. And then our fourth is going to be our methyl. So whenever we draw the arrow, it's going to be coming this way, which is counterclockwise. So remember, for counterclockwise, we have S stereochemistry. So now if we put it all together, we can put S dash. Remember, we want to put it in alphabetical order. So we're going to say 1 diethylamino. And then 5 methyl. Dash 5 nonanol, which can also be written methyl nona nonan dash 5 all. Any questions on this one? Yeah. Because whenever we have NN, that's gonna be when our nitrogen is the parent chain. So on this one, our nitrogen is is one of the substituents, and so we're gonna call it the diethylamino instead of the NN diethyl. Yeah. Yeah. Why isn't it 1,1 diethylamino? So for that one, it's because whenever we have just one nitrogen, we're only gonna put the one number because technically it's only one substituent, even though it has like two chains branching off the nitrogen. Yeah, no worries. Anyone else? Okay, and then going on. So this is gonna be our start of our reaction section. So for the first question, we have HBr in 50 degrees Celsius. So HBr is going to brominate the alkane and is going to have the hydrogen on another one. But because it's 50 degrees Celsius, we actually have to take into account to some to the not the transition, but the resonance. So whenever we would do this, we would have the transition state of a something like this. We would have a positive charge on this, and then we would have the hydrogen attached to this in a Markovnikov addition. So because of that, we actually have two resonance structures. We have this resonance structure, and then we can also resonate it like this is in this positive charge at the terminal position. So whenever we have this, we need to take into account the temperature. And so for temperature, we know that temperature is going to cause the most stable alkene to always form. So because of that, we want the alkene with the most substituents. So the alkene with the most substituents, if we count, the first one, the top, is going to have only one substituent on the alkene, and the second one has two substituents. So that means that is going to be the one where the bromine is going to attach. So the plus charge is going to be where the bromine attaches for the first step, for the second one. So we're going to have the product of our first step is going to look like this. And for the exam, you don't have to put the transition state or the resonance structure at all. You just have to put the actual product of the reaction, but I wanted to go through it. So this one we have the bromine, and now we have NaN3. This is going to be similar to an SN2 reaction. So what it's going to add is an N3 instead of the Br. So we're going to substitute. So for step 2, we have our substituted Br. LiLH4H2O. This is a strong reducing agent, and that's going to actually change our N3 into a NH2. So it's going to become from N3 to an amine. So now we have our NH2, and now we have a primary amine. And for step 4, it's asking us to react it with a ketone under acidic conditions. So whenever we have a ketone reacting with an amine, we have to remember that whenever it reacts with the primary amine, it's going to form an enamine. An imine, and then whenever it reacts with the secondary amine, is going to form an enamine. So because we have a primary amine, this is going to form an imine. So amine plus ketone, and then secondary enamine. So because we want the imine product, this is going to be our what I like to remember for the imine product is that the nitrogen just takes the place of the oxygen in that box. So in that ketone. So we have our nitrogen that's taking the place of that oxygen. So we have like our nitrogen ketone, and then the rest of our product, which is going to be bonded to that CH2CH. So CH2CH, and then our double bond, and then that. So that is going to be our final product. Yes. Yeah, so that's a good question. This is the high temp. So 50 degrees is going to be your high temperature. We want it to be more subbed. Yeah. And then whenever it's a low temp, she's going to put 0 degrees Celsius. And that's going to tell you that you want to use this one to brominate, the less subbed. That's a good question. Anyone else? All right. So on to the next one. This for this one, we have a secondary amine, and we want to react it with the CH3I and the Ag2O. So this is the uh Hoffman elimination. Wow, cannot spell. My bad. Hoffman elimination. And so what we have here, the first step is gonna not protonate, but it's gonna add methyl groups onto the nitrogen until the nitrogen has a positive charge. And then the second step is gonna act as like a bulky base, I suppose, if you wanna put it that way. So it'll act like a bulky base and it'll create the least subbed alkene. So for our first step, this is going to cause the nitrogen NH CH2 CH3 to become have more, I guess not NH anymore. So it would add the CH3 twice. So and CH3, and then we have the CH2 CH3 already. And so this N becomes positively charged. And then for the second step, it's gonna remember it's gonna act like a like an E2 reaction with a bulky base. So it's gonna create the least subbed alkene. So in this case, we can form the alkene on this or this side. So if we form it on the right side, it's gonna have 3 substituents, whereas if we form it on the left, it's only gonna have 1. So because of that, we're gonna be using the left side to be the alkene part. So our second step is going to be this. So that is the product of our second step. And then for our third step, MCPBA, that converts alkenes to epoxides. So we have our alkane, and we're gonna transform that into an epoxide. So 3. So now we have our epoxide, and now we have a Grignard reagent. Remember Grignard reagents, they're going to be in basic conditions. And so whenever we react with an epoxide, we have to attack the least subbed side. So if we look at the two sides of the epoxide, the right side has 1 substituent, while the left side doesn't have any substituents. So that means that the Grignard reagent is going to attack from this side, break this bond with the oxygen, and then kick the oxygen up onto the second carbon. So now we have the secondary alcohol as the final product of the reaction. So we can draw our base like 5 carbon thing with the methyl in the middle, and then we have our OH right, second carbon, and then right here we have our final CH3 that was added from the Grignard reagent. Are there any questions on that one? So in basic conditions, which is what Grignard reagents are in, is going to attack the least subside. So if it was in acidic conditions, which I mean that's like for other reactions like Gilman's, I think Gilman can sometimes be in acidic. So that's for Grignard is always going to be basic. So you're going to attack the least subside. But in acidic conditions, you would attack the most sub. Yeah. Anyone else? Okay. Going on. So for our third product, so for our first step, we have a ketone, and this one adds Br to a alpha position in relation to the carbonyl. So we have the Br in an alpha position. So this is going to be like the base position, and this is the alpha on either side. And so we're just gonna add it onto one. So we'll add it onto the. I guess actually we'll just add it onto the right. Yeah, well, the left side, whatever. So both of the sides are the same. In this case, if it did have a methyl group, like if one side was more substituted, then it would go on to that side. So the if you here, this is going to be the product for this one. But if it was on if there was another side that had more substituents, such as like say this was like a CH3 right here, then the Br wouldn't be on this one, and it would actually go to the right, like this. So make sure that to be careful about that. So then the second step, this is a bulky base. So we have the N structure. I can't remember what that is. I think it might be LDA. But the other one, this is T-butoxide, and T-butoxide we know is a bulky base. So for bulky base, we have for a bulky base, we want the least substituted alkene. So this is going to cause the left side of to form an alkene right here. So our product for this step is going to be like this. So we have an alkene, and then our third step we have a diene. So in our third step we have a diene with the methoxy group in heat, and then if you see what we've just created is could be a dienophile. So whenever we have this reaction, what we can do is all we really need to do is just put it together. So I'm gonna move this over. Usually it's easier just to be able to identify it a little, just like this, so that you can have something to work off of, at least for me. So I know that in this reaction, we're going to have these bonds moving up, like to be the bridgeheads, and then we're going to be the bridgeheads. And then we're gonna have the the other bonds, these ones, we're gonna attach over here like this. And then so whenever we do that, we're gonna have the final product of this. So we know the alkene is gonna be on that side. So we're gonna have our alkene to start. So we're gonna form our bicyclic structure. We're gonna have our 4 carbons and then the bridgehead. And then we're gonna continue it. And this time it's going to be connected to a cyclohexane. So we're gonna close that off, and then we know that this is a cyclohexane right here. And then because this OCH3 is on the I think I put it on the wrong one. So this OCH3 is actually supposed to be over here. My bad. But this OCH3 is where the double bond is. So this is if we just put that right here. Now we have to figure out where the electron withdrawing group is going to go. So this ketone is considered an electron withdrawing group. So we want it to be 1,2 or 1,4 from the OCH3. So whenever we count it, if we were going to go from this way, we would count it 1, 2, 3, and we would only go this far to we would stay on the primary cyclohexane ring to see if it's 1, 3 or 1, 2 or 1, 4. So in this case, it's 1, 3. So we can't have that. So this oxygen is not going to be on this bottom side, and instead the ketone is going to be found at the top. And if we count from here, 1, 2, 3, 4, it's the 1,4 adduct. So the 1,4 is going to be more stable, and so that's going to be the one that we are using for the final product. Are there any questions on this one? No. Okay. Moving on. So this third reaction, this is an NAS reaction. So in this one, this OCH2, CH3, high heat and pressure is going to be almost like an SN2. It's a nucleophilic aromatic substitution. So this is NAS. And so it's going to replace the bromine with this OCH2CH3. So the first step, we're going to have our T-butyl group at the very top. And then on the meta position, we're going to have our ethoxy group. So our next step, we have HNO3, H2SO4 that adds a nitro group onto it. And so in this one, we have to make sure that we look at the strongest electron donating group. And so the strongest electron donating group in this one is going to be our oxygen, because this donates by resonance, whereas this T-butyl group donates by induction. So for this, that's going to mean that our OCH2CH3 is going to be our director. And so it is ortho-para-directing, so it can come onto 3 potential spaces. So we can have our nitro group over here, over here, or over here. So if you notice on the first circle, on the first dot I drew, it's kind of in a position in between the 2 groups. And so there's going to be a lot of like steric hindrance, especially with the T-butyl group up there. So the NO2 probably won't come over here. And then even para to it, the T-butyl group is like so big that it's probably not going to be there either. So we're going to put it at the ortho position beside the ethoxy. So this is going to be where our nitro group is going to go. So our product for that is going to be our OCH2CH3 and then our nitro group right here. So our third step, H2PT, this is going to cause our nitro group to become an amine group. So our third step, our NO2 is going to become an NH2, is going to become protonated. And then for our fourth step, NaNO2 HCl, this is I think it's a new reaction you guys would have learned, but this creates the diazonium salt. So this is like a important reaction to know, because I think it pops up on a lot of finals. So the diazonium salt is formed on this one. So what that means is that this NH2 is going to go from an amine to the N2 plus Cl minus. So this is our diazonium salt. And now we have our OCH3 with the benzene group, and that's going to be added where the Cl is. So in the diazonium salt, we have N triple bond N. So in this case, like N triple bond N dash Cl. So this is why it has plus minus right here. So because of that, what's gonna happen is that this Cl is gonna be broken off, and then the N, the N that was bonded to the chlorine is gonna be attached to the opposite side of this, because this is an ortho-para director. So because this is an ortho-para director, it's gonna direct it either ortho in these positions, but since it's kind of big, it's probably gonna be para. So we're gonna put it in the para position. So now we have if we start with our ends, so we're gonna start with our ends, and then on each side, we're gonna have our groups. So this is gonna be our OCH3. Then on the other side, we're gonna have our the product that we've been making the entire time, and our T-butyl at the top. And I can make it a little bit clearer, just like that. So that is going to be our final product. So step 5. Are there any questions on that one? All right. On to the next one. So this is going to be our last facts question, or facts reaction. So on this one we have a nitrile group, and this is going to be reacted with H3O and 200 degrees Celsius. So what this is going to do is going to oxidize it all the way into a carboxylic acid. So our nitrile is going to become a carboxylic acid. And if you didn't know what this does, if you look at the next one, it's a pretty simple reaction. This is Fischer esterification. And we know that Fischer esterification goes with carboxylic acids. So our first step, if you didn't know, like you can, if you wanted to, and you didn't know like a reaction, you could go further down and see what you would want to react it with. So for this one, we want to create the carboxylic acid, and then the Fischer esterification will create the ester. So we'll start with the carboxylic acid. 1, 2, 3 carbons. 1, 2, 3 carbons. So we have our carboxylic acid. Now for Fischer esterification, remember we just want to get rid of the hydrogen on the oxygen and then add the group that the alcohol is attached to. So for step 2, we have our ester. And then step 3, NaOET, ETOH. This is going to be Claisen condensation. So what this is going to do is this, if we had, let's say, 2 equivalents of this, we have, I always find it easier to just draw 2 of them. O dash O. One thing I always remember is that whenever like one of them would be deprotonated and then the other one would lose its bond with the oxygen and then form their bond right here with where this oxygen once was with that where that minus charge would be. So that bond would form, right? So we're going to draw that out. Not OH. If we were to draw that out, we would have so for step 3, we have our original that we have O methoxy. And then off of that carbon, we have our first carbon, and then that's going to be where our ketone is. Our ketone, and then this is we were going to just so this is going to be where our ketone starts like this, and then we have 1, 2, 3 carbons, and then the benzyl group. So we can do 1, 2. Kind of running out of space, but bear with me. 1, 2, 3. So wait, 1, 2, 3, and then the carbonyl. So 1, 2, 3, and then this is going to be where our benzyl group is, or phenol. So that's going to be our product for step 3. And then for step 4, H3O in 180 degrees Celsius, this is going to cleave off the ester. So we have the beta keto ester, and then because beta keto, so that means that from this ester position, we have alpha right here, and then the beta, and then on the beta carbon, we have the ketone. So we have a beta keto ester, and then this H3O plus is going to cleave from the alpha position, before the alpha position, and that's going to cleave the ester off. So at the end, the final product is going to be a ketone. So we have our oxygen, and then on either side, we count from here, 1, 2, 3, and then on the 4th carbon, we have our phenyl group, 1, 2, 3, and then our 4th, we have our phenyl. So if we start here, 1, 2, 3, and then on the 4th phenyl, like this, and then we'll just copy it on the other side. This is going to be our final product right here. Are there any questions on this? Okay, 1, 2, 3, yeah. Any questions? All right, moving, I suppose. So in this one, it's asking us to provide a clear mechanism. So from this long chain like diketone into this ketone with the alkene beside it. So this is an aldol product. So whenever we have a ketone and then we have the we have like a substituted double bond, this is called an aldol. And so what we have here is intramolecular aldol. So what happens in intramolecular aldol is actually probably going to come into play towards the end because it's slightly different than a normal reaction that we would do to form this double bond. So whenever we would start, we want to first create our this cyclohexene hexene ring. So we were going to do that. We know that NaOET ETOH, this is going to deprotonate one of the carbons. So you have the choice between this carbon, or this carbon. So if we were going to deprotonate any carbons, if we deprotonated the carbon all the way on the left, this would cleave this bond to form, it was going to form over here. And it would just, probably wouldn't come out to be two cyclohexanes. So we're not going to deprotonate that. Then if we deprotonated on this right side, if we deprotonated from right here, and then we would go all the way over here, this would be a 1, 2, 3, 4, 5, 6, 7, and 8 carbon chain. So this would be like a cyclooctane. So we don't want that either. So we would have to deprotonate right at that, right on the left side of this oxygen. So if we were gonna put a hydrogen right here, we could put NaOET. So Na plus O minus ET. And this could take this hydrogen and then leave its lone pair onto that same carbon. So I don't know why I'm writing like steps like this, but that would be our first step. So now we have a something like this. And one thing we can do here is we can do resonance. So we need to draw a resonance structure. So this minus charge can be moved like this so that the oxygen has the minus charge. So that's going to be more stable than the minus charge that we have right now because oxygen is more electronegative. So our next step, we'll just draw this resonance structure. This. Okay. And then what we want here is to create this 6 carbon chain or cyclohexane. So we're going to start, if we number from here, 1, 2, 3, 4, 5, 6. If this minus charge, when it attacked the carbonyl carbon, it would form the 6 carbon chain. So we went ahead and did that, just moved it like this, and then the bond on the oxygen like that. So now we can have our dicyclos. So we have our O, not OH yet. It's just gonna be an O minus. And then our cyclohexane that we have, if we count our carbons, it's gonna be carbon 6, carbon 5, carbon 4, carbon 3, carbon 2, and carbon 2, and carbon 2, carbon 1. Then carbon 1 is bonded to carbon 6. And then, okay, so on carbon 1, we have our our carbon double bond oxygen ketone. So on carbon 1, if we move this minus charge over here, we have our carbon double bond oxygen ketone. And now what we have is our almost final step. What we need to do now is we need to protonate this O minus. So we're going to do off. And now we have our leaving group. So now that we have our leaving group, now we can do our actual aldol reaction. And so one thing that we need to take note of for aldol is that it's not like an E2 reaction. It's similar, but it's not the same. So it is going to take this hydrogen. So if we have uh, the ETO minus, because we just deprotonated the ETOH, so we can take the ETO minus. If that attacks this hydrogen, what we could assume is that it just happens in one step. We just have the double bond form and then the OH leaves. But this is actually not how it happens. This would be like an E2 reaction. In aldol, what we have is that we actually have a middle step. So this hydrogen, it's actually going to donate its electron bond into this onto this side where the ketone is, and then this is going to kick up this minus charge onto the oxygen. So we're going to have a middle step in between. So that's going to look like this. So we have our middle step that looks like this. And then what this is going to do is just it's going to resonate so that the aldol product is produced. So it's going to move back down. And then this double bond is going to move to this side. And then this OH is going to leave because it's a good leaving group. And that is going to give us our final product. Are there any questions on that one? No questions? All right. So on to synth. So for synth, we have a Michael reaction. So on this one, what we have to try to do is we have to get the alpha beta ester the beta keto ester away from the Michael donor. Also, sorry, on this exam there's a typo. This has a fluorine here. It's not just a methyl group, it's a fluorine. So on this one, we have our Michael acceptor and Michael donor. So in this case, we have to cleave it over here. And for Michael, remember we have to have the conjugated ketone. And so on this one, what we can do is we can have the conjugated ketone right here, and then we can have our beta keto ester on the other side. So we've separated our beta keto ester in our conjugated ketone. So what we're going to do, our first step for that cleavage is going to be NaOET/ethanol. And then for our second step, we have to put H3O plus. So that's going to form these two products. This, I suppose. And then plus our Michael acceptor. Like so. And our fluorine right here. So I guess we'll start with the Michael acceptor. So whenever we start with this, our first step that we want to do is we want to get rid of that double bond. So what we can do here is we can use TB-toxide to form the double bond. So an E2 reaction. Sorry. And then right here we can have our bromine. Remember that whenever we are putting our bromine, is that we put it on a position where it's actually going to be able to be used. For example, if we put it over here, our least subbed alkene is actually going to be this one at the very end, the terminal position. So we're going to put our bromine at the in this position. So now we have a bromine that's allylic to the carbonyl carbon. So what we can do here is use Br2 and acetic acid, and that's going to get rid of our bromine. So that's going to make us have our ketone with the fluorine benzene ring. And now what we can do is we can do acylation. So we can start AlCl3, and we can cleave this bond, and we have two separate things because sorry, we can separate them into two separate, one into an acyl chloride. So we have our acid chloride, and then we have our Cl, and then on this side we have our benzene ring. Sorry, benzene ring with our fluorine. So to get rid of the fluorine, what we can do is HbF4 and heat. And that's going to bring us back to our diazonium salt. So we have our diazonium salt N2Cl minus. So after our diazonium salt, we can, to get it, we could use NaNO3/HCl. That is our reaction. And that creates diazonium salt from aniline. So we have our NH2 aniline. And so if we look at this, to get aniline, we could do more reactions, but from the top, it tells us that we can synthesize it from aniline. So aniline is a good starting material, so we can just circle that and be done with that. So now we have an acid chloride. And so what we can do here to get rid of that is SOCl2. This is going to give us our carboxylic acid. And to get our carboxylic acid, we can just use Jones onto a primary alcohol. And we have our primary alcohol like this. It's a 4-carbon chain. And from the top, we want 4 carbons or less alcohols. So that is a perfect starting material. And now from the left side, so this is our Michael donor. And so in this one, we have our, if we were going to, we can cleave this actually, like as if it was going under the intermolecular Williamson. Not intermolecular Williamson, Claisen condensation. So we can cleave it as if it was going under Claisen condensation, and then we can have the NaOETOH, NaOET/ethanol. What am I? ETOH, and then H2O, H3O plus. And remember, that's going to create two esters that are going to bond with each other. So we only have to put one because they can both be the same thing. So we have our ester. And now what we can do here is get rid of the ester, form the the carboxylic acid from the Fischer esterification. So we can put H plus over the arrow to signify Fischer esterification. And then this will add a 1,2 carbon alcohol, so ethanol, plus our carboxylic acid. And we have our ethanol, that's fine. And our carboxylic acid can be formed by Jones one more time. And we have our 2-carbon alcohol again. So that is our synthesis. Are there any questions on this one? Yeah. For Claisen, we have to put the temperature. I don't think so. I don't think we have to put the temperature. Yeah. Yeah, this isn't decarboxylation. Yeah, that's true. Yeah, because we're keeping the ester on. Any other questions? Okay. And so we can go to our final section, our spectroscopy. So in our spectroscopy, this one we have a nitrogen in it, so it's going to be slightly more fun. So for our unsaturation number, our equation for it is going to be 2C plus 2 plus nitrogen minus hydrogen, all divided by 2. So remember that it's plus hydrogen and not minus nitrogen, or plus nitrogen. So we're not going to subtract our nitrogens, we're going to add our nitrogens. So if we put that all together, we have 22 plus 2 plus 1 minus 15. That's going to be all divided by 2, and that's going to give us 24, 25, 10. So we have a unsaturation number of 5. So because we have our unsaturation number of 5, we know that we have our benzene ring, and then we have one more left over. So we have one double bond. So if we keep looking, we go past this. Honestly, I don't like to look at the spec all this often, but I guess in this one it could help considering it has a nitrogen, but it doesn't. So in this one we have a 6 hydrogen that's looking at a 2 hydrogen. So we have CH3 bonded to CH2 twice. And if we keep going, we have these 4 hydrogen that's looking at CH3, and these are quite downfield. So this could be this could mean that it's either attached to the nitrogen or the oxygen. So this could be our CH2 dash CH3. That was a bad box. So these are going to be attached to either nitrogen or oxygen. And if we keep going, we see that we have a doublet structure. So that means we have 2 subs on our benzene. So benzene, 2 subs, para. And then at this, we have our 1H peak, and this is in our aldehyde range. So our 9 to 10 is going to be our aldehyde range. So this is going to indicate that our oxygen is going to be an aldehyde. So what we know about aldehydes is that they take a double bond. So this one unsaturation number that's been missing, we know that that's where the oxygen is going. So now we pretty much have all the things we need to put it all together. We know that all of our oxygen is accounted for. So our oxygen is gonna be looking something like this with hydrogen and probably no carbons, because so we know that our oxygen is looking this carbon is looking at no carbons, because if there was, we'd probably have a downfield stretch where this carbon is looking at a where this like if it was like a CH2, this would be looking at a so we would have a 2 sorry, if this was like a CH2, this would be like a 2H looking at a looking at one hydrogen, so it'd be like a 2H doublet. And unfortunately, other than these ones that we have right here, we don't have any 2H doublets. So we know that there's no CH2 attached to this aldehyde. So this aldehyde has to be connected to the benzene ring. So one of our subs of the benzene ring has to be this aldehyde. So we have our aldehyde. And now if we take a look at how many carbons we have 11 carbons. So right now we have 7 accounted for. And the only thing we have left is four carbon molecules. And each of them, we have 2 of them which are identical, that are both downfield, that are connected to probably our nitrogen now because our oxygen is taken. So we start with our nitrogen. We can put our diethyls right here like this, and that would make sense because our CH2 is looking at our no nitrogen, is looking at our electronegative atom, and is also looking at 3 carbons, giving it the quartet right here. And our CH3 is not as downfield and is looking at a CH2. Both of them are looking at CH2. Both of them are in the same because it's stacked. This is telling us that they have symmetry, and so we have 2 symmetrical ethyl groups. And so that is going to be our final product. So the final product for the spectroscopy is going to be our benzene ring, diethyl, N diethyl aldehyde. Are there any questions on that? No questions? Okay. Then that is the end of the final exam review. So to everyone, good luck, and I hope everything goes in your favor. And y'all can come up for questions now.